We'll speak about a work which has been done in my PhD thesis framework with my coordinator Patrick Franciosi and Dr. Salman, which is my tutor. So I will speak about fiber reinforced materials, and so we have some possibility. We consider we can have these continuous and randomly oriented fibers. We can have the alignment and also continuous and aligned, so a bundle. I will speak about a bundle, a fiber bundle contained in a software matrix, and the aim of this work is to start from the modula of the single phases and via a particular process of homogenization obtain the effective modula of the composite. We will use the properties we derive for describing also different structures. Here we can see the differently oriented planar alignment, or also some 2D networks, and we want to extend it also to 3D networks and so on. We have this kind of structures in nature. Here is graphene, but also, for example, in bone we have at a certain level that we have fiber reinforced matrices, and so this discussion is not only academic, but can be based also on natural research. Why to think to fiber reinforced materials? Because we have the advantages of fibers, so high strength, high stiffness, and a good shear properties due to the matrix. So we can think to arrange the bundle as a 1D regular bundle, and this is the case which we'll study. Or we can arrange it with two regular bundles, or we can imagine also in the third direction. Via the homogenization we derive the effective property estimates, which depends on the multi-continuity of the single phases and also on the interconnections. The interconnections can be physical interconnections, the pantographic case, for example. Here the matrix is devoid, obviously, and this is a 3D pantographic structures. We have 2n layers of pantographic sheets, and we have the pivots, which are physical connections. Or we can think to friction, for example, which is a weaker interconnection between fibers. The main idea is to describe, we won't arrive to that today because it's my PhD work, to describe 2D or 3D networks, and for doing this we start by the description of 1D bundle. So this is the first step I will discuss, and we do it. This is the process proposed by Patrick in a particular homogenization method based on the calculus, on the knowledge of the green operators. We can know the green operators of a single inclusion. I call inclusion one single fiber, for example, here, and the couple, the pair interaction. So we have different green operators to describe the interaction, the single fiber, and via these two specific operators we build the infinite alignment and after the 1D bundle. So we consider the simplest case for give just some hints about green operators. We have the matrix and some volumes in the matrix, I will call them inclusions. And we have the modula, the properties of the two phases. Like in every physical theory in which we have non-locality, we can use the properties of the green tensors. So we have, for example, a body, an extended body, in which in one point of this extended body we apply a force. We want to see the effects, so the displacement, for example, on another point of the same body. These can be described by using green operators. We do it in electromagnetism, in a lot of, also in particle physics we have something analogous to this. If we join this definition with the equilibrium equations, we have linear elasticity here, we can derive the so-called modifying green tensor, which is this, and which is related to the properties of the composite material. We integrate it on the volume of the single inclusion, and we obtain the modified green operator integral, and via these green operator integrals we can build the effective moduli tensor, which is built by the properties of the matrix, the properties of the inclusions, the fiber concentration F, and these two objects. The red one is the operator of the fiber pattern, and the green one is another green operator which is related to the spatial distribution of the inclusions. One interesting interpretation of this or rewriting of this operator is done via the so-called inverse radon transformation, which allow us to rewrite the operator via a term which is a shape function which depends only by the geometry, and another terms which depends on the physics, on the properties of the materials. So if we do this, we firstly calculate this operator for an alignment, and after we turn the alignment we decide how to which kind of simplification we have to do for obtaining the effective properties of the composite material. I show you this figure. We have the operator of infinite planar alignment of cylinders. Here there is a plot in terms of the ratio between the distance between two cylinders and the radius of one cylinder. We can see in these images, we did this for two different values of the Poisson ratio. If we have that the single fibers are really far one from the other, so we have a dilute phase, we have the values which are the same for the single operator for a single inclusion. When we approach the fibers, so the distances, the interdistances are very little, we have that some components of the operator are zero and others instead become different from the single inclusion. And this image clearly shows that we cannot neglect the interactions between the fibers, and also give us a limit of the validity of the interactions, and this limit is more or less 10 fibers. So each fiber sees more or less 10 fibers around it, and when we do the complete calculus for the bundle, we will limit to this interaction zone. We use 4 different models. We use the first one, which is well known in literature, and it's the case of a single dilute of the single fiber in the matrix. So we are neglecting completely the interactions. Or we have a very simple pattern, so 3 fibers. And after we have the complete pattern, they are arranged along an hexagonal pattern. The difference between the 2 last models is that if I consider a stretched or compressed situation, I will define differently the interaction zone. So the second operator, the green one I showed you before, is related to this zone. Here we don't deform it. Here it is deformed as the whole material. And we calculate the components of the green operator for this 4 model, and we compare to a numerical measure I did with COMSOL for different values of the stretched or compressed structure. I show you this is a calculus for a single, for the first one, for a single fiber in the matrix. So we have these different values of the elastic modulus, of the shear modulus of this composite material. And after I will consider the bundle. These are 2 different numerical preparation for the numerical experiment. I should consider a 3D bundle, but it's analogous to this 2D problem if I want to know just the compression along, so the Young modulus along these 2 directions, and the shear modulus if I shear in this direction or in this direction, which should be the same. So I will consider, for example, for the shear modulus only C55, and I will show it for different arrangement of the structure, so for different geometry, which are defined from this parameter eta, which is related to the geometry. It is always an hexagon, the basic cell, but it is an hexagon stretched or compressed. If I calculate the red curve is relative to the numerical calculation. The green curve is the shear modulus C55, which is the one I calculated via numerical. And you can see also the other 2, which can be done by green tensor method. And the black ones are related, so you can see the symbols, the X, the triangle, the little circle, which are related to the other models. Here are defined all the symbols, and it's really clear that the most close to the numerical experiment is the one in which I consider all the pattern, so this, and where the interaction zone rests invariated. So I did this for a concentration of 40% of fibers and 60% of fibers. This is for the shear modulus, and I can do, we did it also for the Young modulus. These points are the numerical experiment, and we have a problem because we do some simplifications. The simplifications is how to choose all the fibers to consider for calculate the operators. If we consider because we have different alignment on the different angular directions, which are more diluted or more concentrated. We can give some weight for the different alignment in the calculus, and we obtain different estimates. So for the Young modulus we have some difficulties to join the numerical values. This is for 60%. But we are working on this, and this was my last slide before concluding. We are trying to generalize these for 3D networks. Now we have the bundle. We want to consider the case of 2D bundles or 3D bundles. Lastly, in the spirit of this work, in which they had this object, which is composed by a matrix, which is a linear elasticity matrix, and the fibers, which are always in a linear elastic material. After the homogenization of this object, they obtain a second gradient material. So an interesting idea is, because it is what I want to do, if I take a box, and so the box is the matrix, and I put in it some fibers in these two different ways. So the fibers are not attached, there is the matrix between them, and I stretch, for example, or I shear this box. Can I obtain something similar to a second gradient material? I think it's very difficult to prove this by mathematics, but we can start. I started to do some numerical simulations via COMSOL, and I obtained this, which seems something like pantographic behaviors, and by changing the properties, the modula of the two phases. Here I show this, which is the division from this side. So you can see there are no pivots between the fibers. There is the matrix. Here is invisible. But the effect of the matrix is something similar to some diluted pivots. So we can join something similar to pantographic structures. We are working to understand it better. Thank you.
The method that you described is very close to the effective field method, which was developed by Canal 11 as the answer to the previous entry. And my first question is, did you try to compare the results of your method and of that method? And what is the difference?
The method of?
Effective field. Effective field method. It's about the same.
Yes, I didn't do any comparison for now. I started to study this. This was new for me, so.
To me, the formula which you present
yes.
for the effective field.
Yes, it's the same. Yes, yes.
And so.
Yes, I think it's the same approach. It was started by Eshelby in also before.
No, after that, it was effective field.
Yes,
then
yes.
you consider every inclusion as an isolated one, as a field of the effective field, which is created by all the other inclusions. All there is two green function for the inclusion and for the symmetry of texture, symmetry of the distribution of the inclusion. Okay, and my next question is that if you have just one family of the inclusion with the same alignment, then this is all this procedure is straightforward, very simple. But if you have different alignments, different families of inclusion, it's very questionable. It's not obvious how you can separate it in that case, and there are many different approaches. And your last picture which you show us, you do something, but what do you assume?
For the last slide, you say? It is a numerical slide, so I did it with linear elastic materials in COMSOL, and I tried to see if changing the elastic modula I can find some behavior like pantographic structures. But I know there are a lot of difficulties to write it via the green operators. Yes, you have to consider the interaction in a different way. We are working on this, so it's the next step. I don't know if we are good to.
Have a look at the wall because they already did something about this.
Okay.
So I have a question,
yes.
A very practical one. What is the contrast of properties between the fibers and the matrix?
Yes, I didn't say that.
And the subsequent question is, do you intend to do experiments?
Okay, in this case the contrast is the shear modulus of the matrix is 1, normalized 1, and the shear modulus of the fibers is 50. Is 50 times greater than the one of the fibers of the matrix. And in this case, instead, I have also other images. I tried to change the duration between to approach a different deformation. So here I don't remember, but I changed it a different way to approach these shapes.
Okay. So one question there.
Okay, quick one. In your procedure, you use something, you set shift function for your transformation.
Yes.
Do you know that? Is it a kernel-like operator, or is it always the same, or do you have to choose it?
I said this here. These shape functions we calculate on the basis of the geometry of the arrangement of the network, and there is a really complicated method by passing some planes which intersect the fibers, and you have to do the integrals. We have the article. If you want, we can discuss with the article, but there is all the method to calculate these shape functions.
Is the article that you cited?
Yes. No. It's the article. This is about this object and the fact that homogenizing this, they obtain a second gradient material. The article is this and is under revision in this review, so I hope it will be soon joinable.
Okay, thanks.
Yes, physical comment. In fiber reinforced materials, use bundles typically. If you make an experiment on bundles,
yes,
you find that the properties, mechanical properties of fiber are quite different from the single fiber.
Yes.
This is due to the interaction. Mostly due to friction rising between fibers, are in this direction and the other direction. So when you say you account also for possible contrast between fibers, can you incorporate some effect of sliding, friction which would be very important for matching results.
Yes, I understand the physical question. I think that in the analytical calculus of ring operators, you don't consider this effect of friction between the fibers when they approach one to the other. In the numerical calculus, you have this because COMSOL knows this kind of things, and in fact you cannot have the same results of the analytical ones, also because you are doing some simplifications, and this is one of the simplifications. The analytical results in case of very close fibers gives some problems because the nonsense of the problem with this kind of method.
Okay.
What's right?
Yes. Yes, yes.
So if there's no more question, let's thank Mario for his contribution.